and we go on to heuristic 8. And this is to do with using a reactor inside of a distillation column. So for reversible reactions especially, consider conducting them in a separation device capable of removing the products as they get formed, and hence driving the reactions to the right. So if you have a reversible reaction, oops, pointer, you see my thing is working properly again. So I can make annotations on the screen. So when we have something like methanol and acetic acid, and we're making methyl acetate, ethyl acetate, looks like methyl acetate. Anyway, that's an ester and water. And if we can remove these products as quickly as possible, then their concentrations remain low, and therefore the reverse reaction is limited. It's not as fast as you would normally expect in a normal reactor. So the conversion would normally be, the conversion in the direction to the right would normally be limited, because the products will rise towards the end of the reactor. But if you can remove them immediately, you get an advantage, and you can go beyond what you would normally consider as your thermodynamic limit of the concentrations of these things. So conventionally, such reaction separation operations lead to a very different distribution of chemicals. As in, if we went to equilibrium with this reactor, we would have some of all of these things in our product. But if we do this in a distillation column, I'll show you. This is acetic acid, which is heavy. Therefore, it goes down towards the bottom. It will drop down. It will increase in concentration towards the bottom of the distillation column. And water is the other heavy component. Methanol and ethyl acetate are both relatively light components, low boiling points, and so they will tend to rise to the top of the column. So this heavy component you will put in at the top of the reaction zone, and it will tend to travel down and react. But as soon as it reacts, it makes water, which can come out immediately from the reaction zone. Methanol will tend to rise through the reaction zone, and the methyl acetate that gets formed will immediately be stripped out of the reaction zone, and therefore in the reaction zone you will tend to have mainly methanol and acetic acid. And because of the distillation column, you can get relatively pure methyl acetate, ethyl acetate, and water out of that distillation column. So it's a really nice system. When Professor Nicol joined the department, this was something that he showed is used in practice less often than you would think. And the reason is the reaction zone and the boiling points of these components have to coincide. So let's say catalytic reactions tend to occur at about 250 degrees. More than that, you get pyrolysis occurring and unwanted side reactions, and less than that, not many catalysts are active at low temperatures. So let's say that most reactions occur at 250 degrees. Then you've got to increase the temperature, the pressure of your distillation column, so that you get an average, because the temperature in this reaction zone is dependent on the boiling point of these components. So you would need to design the distillation column to operate at a suitable pressure, so that the temperature in the reaction zone is suitable for the catalyst. And so that restricts things a little bit, and therefore there's only a limited number of components that would be suitable to operate at the typical temperatures that catalytic reactors operate at. So just to clarify, when you have a reaction zone, it would typically be relatively big pellets of catalyst that act as a packed bed, rather than trays. You wouldn't have trays if you had a reaction zone, unless, of course, the reaction is a heterogeneous reaction. Sorry, a homogeneous reaction where the catalyst, for instance, is in the liquid phase, or if it is an uncatalyzed reaction. But that's not so. That occurs very seldom. Most reactors will be catalyzed reactors. Right, that was heuristic number 8. So now we go on to separations. Yeah, Philip, speak. Speak now, forever hold your peace.
Yes, I just want to ask on heuristic 8, if it's not really applied that much in industry, why is it a heuristic?
Well, all right, let me just say that that was a paper that Willie wrote. So I suspect you would use it if you could. That is true what the heuristic is saying. You would use it if you could. I think Willie's paper was simply to say it doesn't occur that often. So for reversible reactions, especially consider them and hence driving reactions. Such reactions lead to different. Okay, so they don't really talk about that it might be seldom that you get the correct conditions, but yes, it's implied. I'm just letting you know that it might not happen that often. One of the design projects I gave to the 4th years, was it last year's? Included a reactive distillation column. Yeah, it was last year's. And the reactive distillation column made the process a lot simpler, and the students that did that did get very good marks for that process because it was a low cost. It decreased the cost of the process tremendously. But the problem is, yeah, last year they were using DWSim, and then you had to have the ability to do a reactive distillation column in DWSim, which involves programming in Python, so it's not that bad, but it needs some doing. So yeah, interesting. It perhaps occurs more often than I have let on than what Willie in his paper suggested. Oh, Willie, Prof. Nickel. I think Willie likes to be called Willie anyway. Separate liquid mixtures using distillation. Right, so now we're going on to separations. The last one was still distribution of chemicals. And so separations is a really big and important aspect of the heuristics. We're going to be doing heuristic 9, 10, and 11 in conjunction with each other. So separate liquid mixtures using distillation and stripping towers. So distillation is the one that you would generally look at when you're looking at separate liquid mixtures. You can also use stripping towers, liquid extractors, among similar operations. So liquid extractors are those that operate when you have 2 liquid phases. Usually one is an aqueous phase, one is an organic phase. And so when the organics are relatively non-polar, and of course you've got water, which is highly polar, you may get 2 liquid phases, and then you can use liquid extractors. So essentially, you should read heuristic 9 as separate liquid mixtures using distillation. And there are a few other options that you could use. So here we have it. Reactor system, the liquid goes in, separation system. Some of them might be products, some of them might have to be recycled. But that liquid separation system, select from distillation, enhanced distillation, stripping towers, liquid extraction, etc. Now there's going to be a whole, in fact, not half of our course, 1/3 of our course is going to be allocated to looking at separation systems and how to do this, whether you're choosing distillation, enhanced distillation, and these options that we've got over here. So don't worry too much about it, but in 90% of the cases, it's going to be distillation. Right, so I said that we're going to look at heuristic 9, 10, and 11 in conjunction with each other. Heuristic 10, attempt to condense vapor mixtures with cooling water, then use heuristic 9, which means, yeah, you've got your reactor system, you cool it down to, well, in this case, they say 35 degrees C. That's northern hemisphere, where temperatures are cooler and they don't get as hot as here in South Africa. So I've chosen to use 40 degrees C as the minimum temperature you can go down to using cooling water. In other words, I'm saying that cooling water in a typical cooling tower will go down to 30 degrees C, and therefore, with a 10 degrees C difference, delta T min difference in this heat exchanger, we can get a process stream down to 40 degrees C. Okay, and that will condense out some of the liquid, and then use heuristic 9. Here we've got a liquid going down, and we can have a liquid separation system. Select from distillation, enhanced distillation, stripping towers, liquid extraction, etc., as in heuristic 9. So this heuristic is simply saying, after a reactor, you try and cool it down as much as possible with cooling water. You're not going to use refrigeration. So the minimum temperature we go down to is 40 degrees C. Whatever liquid we have, we would use a liquid separation system. Semi-batch, let's think. Could also achieve this. I don't really understand what you're talking about. I wonder if you could put on your microphone and enhance on that one. Now, Luca. Ah, yes, semi-batch reactors can achieve that, because as you, for instance, are if you're producing ethanol in a batch reactor, you can continuously remove it by operating your batch reactor. So the batch reactor might operate at 35 degrees C, where yeast is the most productive. So your fermenter can't go to more than 35 degrees C. If you lower the pressure of that fermenter and you strip off the ethanol as it forms, because it will be the lowest boiling component of that system, you can strip off ethanol as it forms, and you can keep that going. So as a batch reactor, by stripping off the ethanol, you can continuously add glucose as adding nutrients to the fermenter on a continuous basis until essentially you run out of volume. So that is a semi-batch reactor. So yes, well thought, Luca. Okay, so we've done now. This is heuristic 10, where we cool down as much as we can with cooling water, and then we use liquid separation. And now we're going to go on to what to do with the vapor, and that will be heuristic 11. Separate vapor mixtures using partial condensers, cryogenic distillation, absorption towers, absorbers, and or membrane devices. Right. So here we've got a reactor system. If there's liquid coming out of the reactor system, that can go straight to the liquid separation system. If there's vapor, we cool it down to 40 degrees, and then we take off the liquid, and that goes to the liquid separation system, heuristic 9, and we can make our products. But the vapor, we can have a vapor recovery system, and that can produce liquid. As if you, let's say you use a partial condenser. Partial condenser means it's at the top of the distillation column. You don't condense the entire vapor stream. If you've got non-condensable vapors like oxygen, nitrogen, argon, carbon monoxide, you would use a partial condenser, and that would come off as a vapor directly off that partial condenser. The rest of the components that can be recovered will come off at the bottom of the distillation column as a liquid. And some of the products can come off that distillation column as well. So the vapors we take to the purge. I want to talk about, okay, so cryogenic distillation. At the top of this distillation column, maybe I should draw a distillation column. Okay, I don't have to draw that. Think of a distillation column with the condenser at the top, and instead of using cooling water for that condenser, we use cryogenic refrigerant. So we can go with a refrigerant. Let me draw one. A rectangle for our distillation column. A circle for our condenser, a circle for our reboiler, and then we can have a few lines. Okay, that one is going, that's the one of the products, and that pretty much, whatever. So if we use refrigerant over there, then we can make sure that we can condense whatever low boiling components there are, instead of using a partial condenser, and a partial condenser will take off a vapor stream off the top. So instead of using a vapor stream, you can use a cryogenic condenser, which means it's less than the temperature of cooling water, and you can still make your separation. So that's the cryogenic. An absorption tower is, for instance, let me get my pointer. And start deleting. Is when you put in some a liquid, let's call it water for this case. In this case, I'm just going to choose a different color. How did I choose the color? If this is, there's the color. Right. So let's say water goes in over here. Oh yes, and water comes out, here. Then this would be gas coming in, and that would be select. So there's the gas coming in, and there's gas going out. Now let's think of that DW simulation where we had methanol and synthesis gas. If we put in that the vapor portion, so what we did with that methanol, we put it into a vapor liquid separator, which is essentially this thing, at 40 degrees C, and we got the methanol coming off here fairly pure, so we didn't even have to separate. The vapor had some methanol in it, but it also had a lot of synthesis gas. So we can put that synthesis gas through a packed column. And wait, you need a pointer. Through the packed column, and the water enters here. Let's say the water enters here from the left to the right. It trickles down the packed column, and it exits to the right over here, the red. That would be the water. This is the gas stream coming in with synthesis gas and methanol, and the methanol is going to be adsorbed by the water trickling down. And here we will have a water methanol mixture. And that can go into a liquid separation system to recover the loss of the methanol. The stuff that comes out here is seeing relatively pure water. So it will contain virtually no methanol at all. And therefore, this will just be the synthesis gas that will be going out. And then you can consider how to separate the synthesis gas. Let's say that you want to take out the hydrogen. You can use membrane separations. So that is there, the membrane devices. Okay, so that's an absorption tower. An adsorber is very similar, except now, let me just go back to my pointer. I selected, delete that this whole column, pointer, this whole column is filled with molecular sieve, which is a molecular sieve is a zeolite that has got very specific pore sizes that will adsorb specific size of molecules. And so you can have an adsorber, a molecular sieve that's going to adsorb hydrogen, for instance. Usually often they're used for adsorbing water. And by the time it comes out there, you've got only the gases without that substance that you're trying to recover. Trouble with adsorbers is that you have to have two so that you can switch the process stream from adsorbing to the next one, and then you can desorb by reducing the pressure or increasing the temperature of the whole column. Right, let's have a look what Gareth wants to ask. Assuming the need to distill and require the addition of something else, how would we separate the added mass agent from the other component? If it's even necessary. It is necessary. If you're going to add what we call a mass separating agent that helps the separation occur, you've got to recover it. But you can use distillation. You can use normal separation techniques to recover that. You're going to choose it so that it is easy to recover. Is there a preference for a membrane? Condensers in series or another distillation column down the line before we pump back the mass separating agent into the main column? Yes, there's a preference for a normal distillation column. So when you choose a mass separating agent, but let's talk about it when we get there. Gareth, you've had the advantage of going through this course before. Not that you failed, just for the rest of the class's knowledge. You just had the time to swat up a little bit. So stop showing off. All right. So we are done with heuristic 11. Let's just go through it again. We talked about separating vapor mixtures using partial condensers, cryogenic distillation, adsorption towers, adsorbers, and or membrane devices. Membrane devices we have spoken about. I do want to speak a little bit more about membrane devices. They work on two separate principles. And the one is dissolving on a solid surface, essentially. So so permeability is a constant for a certain membrane that says how quickly a gas will pass through the membrane. A given gas, like let's say oxygen, will pass through a given membrane given a certain partial pressure on the one side compared to the partial pressure on the other side. So there's a partial pressure driving force for a membrane. That permeability constant depends on the size of the molecule and how well it adsorbs or dissolves, so to speak. I'm putting dissolved in inverted commas. what is the adsorption affinity of that molecule in within the membrane on the solid surface of the membrane. So hydrogen, I said, would be easy to separate because of its small size, and hydrogen has an enormous diffusion coefficient. So the diffusion coefficient and the size are two things that go together in a membrane separation system. But the other one is how polar it is, because the polarity of the molecule will affect how sticky it is as it's passing through the membrane. So more sticky, in other words, a more polar molecule is not going to pass through the membrane as easily. Okay, let's go on then. Heat transfer in reactors. So that was separations. I have said we are going to go into separations in much more detail, where we talk about mass separating agents, where we add a new component so that we can help separations occur more readily. Yes, Philip.
Prof, I just want to ask, what's the reason that we will prefer to not separate two vapors, but first try and make it liquid and then separate? Is it much cheaper and easier, or is there another reason?
Okay, so you've got to decide, how are you going to separate the vapors? Let's just go back to those options that we had there. If you can use an absorption tower, like use water, and one of those vapors is particularly polar, then that would be a really good way of doing it. The trouble with an absorption tower is, let's say you're using water to strip out one of the gases. You've still got to separate that with liquid distillation. But liquid distillation is a relatively simple unit operation, so that doesn't bother you. But separating gases is always difficult. So certainly you'd want to do absorption if you could. But now let's talk about synthesis gas, and we're going to have that opportunity to look at synthesis gas. I'm going to in Friday's DW Sim TUT, I want to do a TUT where we put in a Gibbs reactor to make synthesis gas at a given temperature. And with synthesis gas, we will always have carbon dioxide and carbon monoxide and hydrogen. And carbon dioxide is pretty much a byproduct, but and water. There's the water gas shift reaction, but water is easy to remove. I mean, you just cool down the gases using cooling water, and most of your water is going to condense out. But now, to separate CO2, CO, and hydrogen, what can you use? Because the boiling point of those things is so low that you can't put a you can't, even with cryogenic distillation, you're talking of minus 80 degrees C just to condense out CO2, I think. So it becomes practically very difficult. How do you get your utility at that temperature? Yes, you do use the Joule-Thomson effect, and that's how they separate air. So there are ways. And palladium catalyst membrane, there are many different ways, but they become fairly specialized separation techniques because it's not distillation. And there are very many ways that you can do it, but it becomes expensive and difficult.
Thank you, that makes sense.
Right, let's go to heat transfer, and we've got 20 minutes and we'll be done with that. Heat transfer in reactors. is better discussed in the context of heat and power integration, and that is essentially what you're going to be doing in CPS 420 next semester. You'll be doing CPS 420 in the first 2 months of the semester. In other words, it's a 8-credit course that covers a quarter rather than a semester. A quarter is half of a semester. So heat transfer is better covered in those lectures 6 to 8. In other words, CPS 420. It is treated here because many methods dealing with heat transfer in reactors also affect the distribution of chemicals. That says what distribution of chemicals the reactor can produce, because if it goes to a very high temperature, you'll have a different distribution of chemicals than a reactor that's kept at a low temperature effectively. So let's talk about exothermic reactors. They're the most common. And here we talk about a highly exothermic heat of reaction. And remember what I was saying yesterday. A highly exothermic heat of reaction is, for instance, if the adiabatic temperature rise is more than 200. Let's consider combustion. You've probably done combustion reactions in first or second year, where we've got a fuel and we've got oxygen, and the adiabatic temperature rise is in the order of 2000 degrees C. But because of running these things with excess air, excess oxygen, you've got nitrogen, which is an inert that is absorbing some of that heat, some of that temperature rise, and you will operate a furnace which is burning fuel at about 1300 degrees C, the flame temperature. So that is a highly exothermic reactor, of course. So when you've got that, consider the use of excess reactant, which is nitrogen with the oxygen. So of course, air is much cheaper than separating the oxygen if you've got a combustor. And so rather use air. An inert diluent, which is nitrogen, and cold shots. Cold shots, I'm going to get my drawing tools out again. Rectangle, red. There's our reactor. And cold shots, we're going to use lines. And we're going to use blue lines because they're cold. You can put in your feed over there, and then the reaction will heat up because of the reaction, because of the highly exothermic reaction. Then you put in some more cold feed over here in the middle of the reactor, and some more all along the reactor, and that's called cold shots. And that cools down. So this goes up to, let's say, 300 degrees C due to the heat of the reaction. You put in some more cold reactant at 25 degrees C, and it cools down to 200 degrees C. It rises again to 300, cools down, and rises to 300, cools down to 200, rises to 300, all along the reactor. So that's what you're talking about, cold shots. These affect the distribution of chemicals and should be inserted early in process synthesis. In other words, you must know what reactor you're going to use early in process synthesis, because when you do this, you might get a different distribution of chemicals. You might have different products. That would be red anyway. That would be a hot stream coming out there. But doing it this way will be different compared to using a whole lot of nitrogen as your feed to prevent the thing getting too hot. So what you see here in heuristic 12, highly exothermic, you don't even try to use indirect heat transfer. You're not going to put in heat transfer tubes if it's a highly exothermic heat of reaction. You've got to use these other methods, because otherwise the temperature rises far too quickly, and you can get a temperature runaway too easily. For less exothermic heats of reaction, circulate reactive fluids to an external cooler or use a jacketed vessel or cooling coils. Also consider the use of intercoolers. Now, let me see if I can get a black whiteboard from here. No, it's not here. We have to go to share blank whiteboard. Right. So, with less exothermic, you can use indirect heat transfer. Indirect heat transfer is where you've got tubes that are separating your process fluid from the cooling fluid. So we choose some shapes, a few rectangles. Hey, who's drawing on my whiteboard? No, maybe it was me. Right, so those are the things they talked about, and the let's do the one way of cooling down a reactor is to put a cooling jacket around the reactor. So there's the cooling jacket, and you can have your let's use a pencil. You can have a shaft there. Isn't that a beautiful straight line? And that's your reactor. You can have your inlet coming. You can have the inlet coming in over here, and the CSDR and the outlet coming out there, and you can have cooling in that way. You just got to be careful about scale up, because this area of cooling increases with the square of the volume, or the volume flow rate. And as the volume flow rate increases, let's say you want to keep the residence time the same. As the volume increases, this as the mass increases, the volume increases to the cube, and therefore the heat of reaction, number of kilowatts exothermic heat of reaction, increases to the cube of the dimension, and this increases to the square of the dimension. So that is something to keep in mind. The other way, you can get more area into your reactor if you use cooling coils. So you can have a coil that runs on the inside of the reactor. And I'm going to take it out that way, left to right, and that way you can remove the heat of reaction. And it's also pretty much, you can only have that much area of coil. Double coils don't work so well because you don't get such good mixing. If you've got a single mixer in here, double coils do not work as well. So yes, you do get a little bit better than scaling of coils in a reactor than in this one. But probably the better way, and this is the one that we showed in our example of making vinyl chloride monomer, is that we put in a heat exchanger and we recirculate through that heat exchanger. Like that. So you can just remove the heat, you cool down the liquid goes back into this CSDR essentially, and you can cool down, you can make that heat exchanger as big as you like, and you can have the recycle as fast as you like, and you will still manage to keep that reactor cool enough. So those are the three options I talk about. Now I'm going to go back to share files. Ooh, share now. And it should take us back to where we were. not so easy. That's where we were. For less exothermic heater reaction, circulate reactive fluid to an external cooler, or use a jacketed vessel or cooling coils. Also, consider the use of intercoolers. I'll show you the intercoolers. This is highly exothermic heater reaction. You can use excess reactant, and therefore you'd have to return the reactant, or an inert diluent, and that could be, for instance, water, and you could return the water. And cold shots, where you keep on adding them throughout the length of the reactor. It could be separate reactors, adiabatic, but those sections are adiabatic, and those are for highly exothermic heats of reaction. And then for less exothermic heats of reaction, here's the reactor, there's the cooler where you recirculate the thing, and you can have a control system that controls this rate of cooling so that you get the right temperature, and so it's a nice easy thing to control. Intercoolers is much like that cold shots, but this is something that you'd use only if you have a less exothermic heat of reaction, that you'll have an adiabatic reactor and then cool down with a heat exchanger. So you use indirect heating, indirect cooling, and then you allow the adiabatic temperature rise again, cool it down, and so forth. This, of course, is a very good way of scaling up, because you will have, as a CSTR, if this were a CSTR, you would have an equal temperature all the way through this reactor, and so whatever you do in the laboratory will be totally mimicked in your plant. You can operate this and control it at exactly the right temperature very nicely. Similarly, this one, you can set up a laboratory experiment where you raise the temperature exactly according to an adiabatic reactor. So you don't have to, not even laboratory, on a pilot scale, for instance, you can have these sections where you where the temperature rises throughout the reactor adiabatically. And therefore your laboratory or pilot plant results are going to mimic the large reactor quite well. So this is a bit more expensive because there are many heat exchangers, so you don't get economy of scale. Many reactors, many reactor sections. So compared to if you have a single reactor, you get some economy of scale. A single heat exchanger, you get economy of scale. Now, endothermic reactors, exactly the same. To control the temperature of a highly endothermic heat of reaction, use all of these things. Excess reactant, inert dilute, or hot shots don't involve heat transfer, indirect heat transfer. In other words, heat transfer through tube, through a heat exchange surface. They affect the distribution of chemicals and should be inserted early in the process synthesis. Less endothermic heats of reaction, circulate reactive fluid to an external heater, or use a jacketed vessel or heating coils. So again, all of these use indirect heating through a surface that separates the heating fluid from the reactive, from the process fluid. And also consider the use of interheaters, and the interheaters are exactly the same principle. All right. So we don't have, it's exactly the same principle as this, except these are coolers, and we would want heaters. If it was endothermic, we would have interheaters, and the temperature would start hot, endothermic heater reaction, cool it down, you heat up the stream, start hot, cool down, heat up the stream, and so on. And that's it. Much easier than than in reactor design. Just a few ideas for heat transfer in reactors. Yeah, and that's it for today's lecture. I'll switch off the recording and invite questions.